Maintaining the proper assortment and quantity of the thousands of different chemicals in your body and monitoring how those interactions of the chemicals go on with one another is one of the most important aspects of homeostasis in the human body. We saw in the last chapter that the chemical level of organization, which remember was the lowest level of structural organization, consists of atoms and molecules. These letters of the anatomical alphabet combine to form body cells and organs and then systems of astonishing size and complexity. In this chapter, we're going to consider how the atoms bond together to form molecules and how atoms and molecules release and store energy in processes known as chemical reactions. We're also going to learn about the importance of water, which accounts for almost 2/3 of your body weight, and the water's importance in chemical reactions and the maintenance of homeostasis. And then we're going to look at several groups of molecules and their unique properties and look at the macromolecules that are important in the human body and how these molecules and the processes that form and maintain them help to keep you alive. So we'll begin by looking at how matter is organized and getting some basic terminology. So chemistry is the science of the structure and interaction of matter. All living and non-living things consist of matter, which is simply anything that occupies space and has mass. Mass is the amount of matter in any object, and that doesn't change. Weight, on the other hand, is the force of gravity acting on matter, and that does change. When we're farther away from the Earth, the pull of gravity is weaker, and this is why things such as astronauts weigh less when they're in outer space. Pretty cool, huh? Matter exists in 3 states: solids, liquids, and gases. Solids, such as bones and teeth, are compact and have a definite shape and volume. Liquids, such as blood plasma, have a definite volume, but they assume the shape of whatever they're in, such as a blood vessel or inside the heart. Gases, like oxygen and carbon dioxide, don't have a definite shape nor a definite volume. All forms of matter, both living and non-living, are made up of a limited number of building blocks called chemical elements. Each element is a substance that can't be split into a simpler substance by ordinary chemical means. Each named element is designated using a chemical symbol of 1 or 2 letters. Some of the more common ones that we're going to see in the human body are oxygen, carbon, hydrogen, and nitrogen. So these elements make up the majority of our body. You'll also see that some of the elements are going to have sort of strange symbols. I mean, it's pretty easy to see how O is oxygen, C is carbon, H is hydrogen, and N is nitrogen. But then we have things like mercury, which is Hg, and sodium, which is Na. Well, obviously, those are not the first couple of letters, but they come from the Latin or Greek or any other language that was used to name those particular elements. So not all of them are quite as straightforward, but we'll use several of these throughout our study and they'll become very familiar to you. Each element is made up of atoms. Atoms are the smallest unit of matter that retain the properties and characteristics of that particular element. Atoms are extremely small. If you think about when you're reading your textbook and you see a period at the end of a sentence, about 200,000 atoms of the largest atoms would fit on the period at the end of that sentence. There are several subatomic particles that make up atoms. However, we're only going to consider 3 that are the most important in maintaining chemical reactions in the human body. So within the nucleus, or the core of each atom, you have a certain number of protons that have a positive charge and neutrons that have a neutral charge, so they're neither positive or negative. Outside of that, you have electrons that have a negative charge. Now, if you look here, you've got 2 different representations of atoms. So these are the 2 that are most commonly used. The electrons don't maintain a definite place in space, but they travel around the nucleus. And so sometimes you will see their sort of sphere of travel represented by an electron cloud model. However, when we're drawing it out and discussing the electrons and their importance in chemical reactions, it's often much easier to use the electron shell model so that we can show where those electrons would potentially be located. So here you see an atom with 2 electrons on the innermost shell and 4 electrons on the outermost shell. The number of protons in the nucleus of an atom is the atom's atomic number. Atoms of different elements have different atomic numbers because they have different number of protons. For example, you see here an atom of carbon. Carbon has 6 protons in the nucleus, so its atomic number is 6. The mass number of an atom is the number of protons plus the number of neutrons in an atom. So you see here in our example of carbon, we have 6 protons and 6 neutrons, so a mass number of 12. Now this is in the normal atom. There are times when we have a different number of neutrons in the atom, in the nucleus, and those create isotopes. So isotopes are atoms of an element that have a different number of neutrons, so their mass number is different. This does give some of these atoms different properties, some of which are radioactive isotopes and can be used in radioactive medicine and also in imaging studies, and have many different clinical uses for imaging and for tracing, and also delivery of some types of medication that need to be targeted to specific tissues in the body. On this slide, you can see the atomic structure of several of the common atoms that we're going to be talking about as we study the human body. The atoms of different elements have different atomic numbers, remember, because they have different number of protons. You can look at each one of these and you can see their atomic number matches the number of protons. Okay, their atomic mass is the protons plus the neutrons. Do you remember which of the 4 of these was the most abundant in living organisms? That's exactly right. The one's on the top. Sodium, carbon, nitrogen, and oxygen. We will be seeing a lot, hydrogen, carbon, nitrogen, and oxygen. We will be seeing a lot of sodium and potassium and chlorine as we continue talking about the body as well. And in your Anatomy 2 class, when you start talking about hormones, iodine will also be very important. What you can also see in these images are those electron shells. So if you'll notice, the innermost shell of all of these, except for hydrogen, has 2 electrons. The second electron shell has 8 electrons. The third has 8 electrons. And then once you move past the third, you get out into electron shells that can hold many, many, many electrons. But this of the second electron shell holding 8 electrons is what is known as the octet rule. So the octet rule, oct, remember, means 8, means that that second electron shell is full. We talk about that when we're talking and looking at the way that some of these chemical bonds are formed, and the number of electrons in that shell helps to create how reactive or how likely these atoms are to form bonds with other atoms and create molecules. All right, so we'll move on and talk about some more terminology here. We're going to discuss quite a bit about ions. Ions are atoms that have either gained or lost electrons. Okay, that has to relate back to that octet rule. Remember, we talked about that second ring for electrons being happy and satisfied, being full when it has 8 electrons. Well, if it only has 7 electrons, it really wants to get 1 more. So it's going to try to steal electrons from another atom so that it can get a full electron shell and meet the octet rule. Another atom, perhaps, that only has 1 electron in that second shell is going to be more likely to give up that 1 electron than to try to gain 7 more. So when this happens, this creates the gain or loss of an electron and creates an ion. An ion is a charged particle. Remember, those electrons have a negative charge. So if you gain an electron, if an atom gains an electron, it has gained 1 negative charge. So that makes it a charged particle, and by definition, an ion. An ion that loses an electron has lost one negative charge. Therefore, it becomes positive, because remember we said that the number of protons positively charged is going to equal the number of electrons, the negatively charged. So when they gain or lose electrons, they then become charged particles. A molecule is where you have two or more atoms that are going to share electrons. Some of the more common molecules that are formed in the human body are molecules of oxygen. O2, two atoms of oxygen sharing electrons. You also have hydrogen and oxygen that share electrons and create water. Compounds are substances that can be broken down into two or more elements. So sodium chloride, what we commonly call table salt, is made from sodium and chloride, chemically bonded together by sharing electrons.